Astrophysicists have a hard time getting distances.
Distances is everything.
Pictures of something in the night sky, seeing the sort of 2D sky, if you will, from Earth is great.
What
but
sky? Oh,
the
2D.
two-dimensional.
2D. Mm-hmm.
But getting distance to that object is very challenging.
And once you get the distance, then you can create a journey through it, right?
That's right.
Okay, so now it's not just visible light data that you've got, because we've got telescopes in every band of light of the electromagnetic spectrum. We have ultraviolet telescopes and infrared. We got a telescope in every band that we cannot see. So what do you do with those data?
We show them.
How do you show them if we can't see them?
Well, that's the challenge.
Actually, I know the answer to that question, but I want you to say it because you've got the title manager of the digital universe.
How do you reconcile showing something that we should be seeing with our eyes, visible, like the stars in the sky, with something that is invisible to our eyes?
That's what I'm asking.
Like?
How do we
yes, thank you, Lynn.
What's invisible?
Like microwave radiation or infrared or ultraviolet.
Right, so how do we see that? How do you make it visible to us?
The scientists, and we take and... Our third
You're the manager.
Guest here.
You're the manager. I want to see the manager on this.
I want to see the manager. I want to see your manager.
Take me to your leader.
For real, I want to know.
We essentially decide how it looks. You get a sense of how it looks from the instrument, and then you decide how you want that to look. And that relates to how we see things as humans. So it's always a judgment call. So
you're converting invisible light into light that we can see, but then you have to be honest and say, you actually can't see this. This is what it would look like if you could see in those bands of light, correct?
Exactly, yes.
Like when they tell you this is how a dog sees things. You don't really know that.
I guess not. But you can study.
Yeah, but somebody has to decide what would it
Somebody's
look
got to make
like
that judgment.
on the scientific data that they have.
Somebody's got to make that judgment.
Exactly.
Then you need to make a dog hearing simulator or a dog seeing simulator.
Right, which is essentially
that guy?
That's essentially what you've done, Brian.
Universe, yes.
You've made a simulator that allows us to see in bands of light we cannot.
Correct.
And so what's your favorite data set in a band we can't see?
Well, I love the W map.
The W map. So this is of the microwave
radiation
of the entire universe.
The baby picture of the universe.
Of the universe, born. The light cast forth
13.4 billion years ago.
So you're just digging it.
So the Big Bang picture, like when God said, "Let there be light,"
baby
you're
pictures.
like what it looks like when it turned it on.
Well, it's as far back as we can see.
I know. I'm with a room full of scientists. Oh God, what does that mean? Okay.
What we're going to do when...
Can we talk about other kinds of light?
What's that? Yes, we can. We'll do that, in fact, when we come back. And when we come back, we have yet a third guest I'm going to bring into this circus.
I hope you have a stick of butter. There's no room for all of us in here.
We'll see you on Startalk Radio when we're back from this break.
Good show.
Let there be light.
The future of space and the secrets of our planet revealed. This is Startalk.
Wrapped up like a deuce under the runner in the night. Blinded by the light. Wrapped up like a deuce under the runner in the night. Blinded by
It's amazing how much astrophysics there is in pop music. You are back. We are on Startalk Radio. I'm your host, Neil Degrasse Tyson. Let me reintroduce my guest, Michael Benson.
Stairway to Heaven, for example.
Michael Benson, journalist, photographer, space geek all the way. And not a month goes by where I don't read one of your op-eds or editorials criticizing NASA and the nation's priorities. Maybe we'll get back to that a little later.
Wow, there is some weird tension with you guys.
Brian Abbott, manager of the Digital Universe at the Hayden Planetarium. Thanks for being on Star Talk. And, of course, my inaugural co-host, Lynn Koplitz.
There's weird tension between you two.
The light of your life.
Well, yes.
Second light.
So we are here talking about Let There Be Light, the light of the universe, and how it's created, what it's all about. Let me just sort of reset some of the physics of what's going on here.
I have some questions.
Sure. So light is energy. It's a form of energy. There are a lot of kinds of energy. There's kinetic energy of motion. There's potential energy. You get that in where you are in the universe. Or you can have chemical potential energy. That's the energy that shows up when a bomb explodes. But in the universe, light is a form of energy, and we call it electromagnetic energy. And
that's from the Big Bang?
Yeah. So at the Big Bang, you have all of this energy in a very small volume, and it is so hot. It is so energetic that matter is forming out of the energy according to equals MC squared. And the matter that's
according to the Bible, God just says, let there be light, and then the light turned on. But you're saying
yes,
he
I'm saying
threw
something
a bunch of crap
different
together.
from that.
Okay.
I am indeed saying something different from what you read in Genesis. Yes. So what we have here is this soup. It's a matter-antimatter energy soup. And then as it expanded and cooled, all the matter and antimatter particles collided with each other and annihilated and created light. Except some matter was left over out of this. 1 out of 100 million particles was left over, and that is the matter that you and I are made of. And all the other matter-antimatter collisions created the light of the universe, now visible as microwaves. At the most distant regions of the universe, we call it the famous microwave background, the baby picture of the Big Bang. And so this is light. It all travels at, of course, the speed of light, which in miles per second, 186,282 miles per second. And if you want to get really geeky at home, one nanosecond, that's a billionth of a second, light travels 1 foot. So if you're standing a foot away from someone, you can say, I see you not as you are, but as you once were a billionth of a second ago.
So if you were going to time travel, would that be the speed of light, like in Back to the Future?
Will it be exactly? Yeah.
I like my really serious
Great question.
Look at all of our science, all of our really smart people in the room. We're like, well, who is this hooker and why is she in
it's
here?
exactly like that minus the flux capacitor. Yes, So telescopes are kind of like time travelers because as you see far out in space, you see far back in time. I see you as you once were, like I said, 2 billionths of a second ago. You're 2 feet away from me. You are younger as I see you than you are at that moment that I see you. Yes.
You just said that.
Yes. The moon is like a little more than a light second away. The sun, 500 light seconds away. We have galaxies. Here's a cool one. We have galaxies that are 65 million light years away, which means if they had a powerful telescope, they could look to Earth and they can see the dinosaurs going extinct as it's happening, as it's unfolding.
You're blowing my mind.
They would need super duper telescopes for that.
Can we go back to something simple for a second?
Well, what's that?
Because let's break it all down for me. Okay.
Yeah.
First of all, like you said, light and energy. Is that why we can see lightning?
Well, so lightning is a lot of energy in a small spot, which rapidly expands the air and it creates basically a shockwave. So you hear the thunder, and it's it rapidly expands the air, and it's a shockwave. Okay, and so that's why you hear it. And, of course, you hear it later than you see it. But it is very high temperature, and when you bring anything to high temperature, it glows. You see the sun, because it is at a high temperature, it glows. You heat anything to high enough a temperature, it will glow, period. Whether or not it's a gas, solid, it'll glow. That's correct.
How interesting.
And there's a guy from the 19th century who put together all our current understanding of the behavior of light. And he's called Maxwell, James Clerk Maxwell. And they're called Maxwell's equations, one of the most beautiful set of equations there are in all of physics. Have you ever heard of Maxwell?
No. You know, the only Maxwell I know is
checking.
the coffee guy.
No, I'm just checking. In fact, I don't know if it's the same guy. Probably not, though. My guess.
Who discovered X-rays?
Who discovers X-rays? Wilhelm Röntgen. In fact, in Germany, they're not called X-rays. They're called Röntgen rays. Yeah, so they still.
Rays?
I don't know if I'm pronouncing any Germans out there.
Thank for my mammogram.
Yeah, basically Wilhelm Röntgen. And it was actually discovered quite by accident. He was working with sort of high-energy emissions from tubes, and his hand happened to be in the way of a photographic plate, and he developed a plate and saw his bones on that photographic.
That's creepy.
It's completely creepy. I would have freaked out if that had happened. And so
then he did it again?
Not knowing that this is the kind of things you die from, too much exposure to X-rays. You've been in the X-ray room, and what does the X-ray technician do right before they flick the switch?
They all leave.
They leave, close the door, shut the door. That's what they do.
The CAT scan's the worst. They go down the hall and talk to you through a thing. They're like, "Are you okay?" "No, I'm not okay. I'm alone in obviously what's a really frightening room." These
are just bands of light that actually are in our everyday life. So your cell phone uses microwaves.
Tell me this, because and now I've got all of you here in this little light summit meeting. I want to know. When, I travel all the time when I'm on the road, and I'm going to be doing it this week. Wednesday, I'll be at the Orlando Improv. Okay. But anyway, my question is this.
And for those who are listening on time delay iTunes podcast, Which
I don't
Wednesday
know
was
what
that?
day
Yeah,
it
that
is.
Wednesday's
Yeah,
like a month in the past
June.
by
It's
then. Okay.
somewhere in June. Whatever. Just go online and look for it. But the Orlando Improv.
It's a light delay.
But here's my question: they're making me now at the airport walk through those body scan things.
Yeah, that's where someone else sees you naked, and the person that sends you through doesn't see it. Yeah, they try to split the person who knows who you are from the person who sees your body
I don't
parts.
care about people seeing me naked. That is enough of that. If someone wants to say, by all means, they can take a look. But I'm more concerned. Like, can it kill me? Like, how? Why does this light hurt us?
I haven't formally studied that scanning process, and
So you don't know? That means DK in genius speak.
what they don't know. Yeah, so they claim that it's not any more dangerous than a plane flight that you might be taking. Your
You guys
exposure to radiation on that, Brian.
This is exactly what I've heard. That when you fly in a plane, you're actually exposed to more radiation than you would be on Earth.
Right, on Earth's surface, because the atmosphere protects you it shields you from a lot of radiation that's coming from space.
Exactly.
That's right. And notice that the doors of it are open. By the way, in your microwave oven, which also uses microwaves. By the way, I should have led off by saying, what's the difference from one band of light to the other? The length of the wave itself. Microwaves are about a half an inch, a third of an inch long in a little wave shape. So if you want to block microwaves, just put a screen where the mesh is smaller than that size, and the microwaves can't get out. So take a look at the door of your microwave oven.
Got that screen.
It's a screen that's got holes. Why doesn't the microwave come through the holes? Because the wavelength is bigger than the holes themselves. And are you old enough to remember how people used to receive TV signals? Rabbit ear antennas?
Yeah,
exactly. Why are the antennas that long? They're about a meter, about a yard long. That's the length of a radio wave. Radio waves are longer than microwaves. And you want to capture radio waves, you get the antenna has to be about that length. So walkie-talkies, which use microwaves, how big is their antenna? It's much stubbier. It's like, it's like an inch.
Wait, if they use microwaves, then can't that be bad for you to